All right, here we go. Welcome to CS 161 lecture number 11. I think it's 11. I didn't double check the question, but I believe it is. Today we're talking about Bitcoin. And right off the bat, this lecture is not in scope for the midterm. So if you would rather leave and go study for the midterm tomorrow, that is totally fine. We completely understand. Just note that this content is in scope for the final. So you will want to catch up on this lecture at some point if you decide to miss it today. But yeah, bring us straight into announcements. As I mentioned, midterm is tomorrow from 5 to 7 if you're taking the normal time. If you filled out the conflict form, we should have contacted you already with your alternate time zone, with your alternate time slot. If you can't make this time, please fill it out like literally right now, and we'll do our best to work out an alternate time for you. So yep, and Monday or homework 3 is due today. It also contains the logistics for the exam itself, as well as a practice exam on the same tool that you'll take the actual exam on. So please do finish it so that you're familiar with exam procedures and whatnot. Okay, so last time we talked about certificates. This is just when you sign a statement that says, oh, this public key is associated with someone's identity. And we're going to see a lot of signed statements when we work with Bitcoin today. When we talked about the trusted directory, so one server basically signs certificates for everyone, but this isn't scalable and it's a single point of failure. So it's not really something that we see in the real world. Instead, what we deal with are certificate authorities. So we have multiple roots of trust. These can delegate their trust. They can sign certificates saying, I trust someone else with their public key to sign certificates that are valid. And to revoke things, certificates contain a expiration date, so a certain time at which the certificate becomes invalid, as well as a specific list of revoked certificate that the CA signs in order to say, hey, the certificate isn't valid anymore. As mentioned in the chat, for the exam, you'll receive your Zoom proctoring links probably tonight or sometime tomorrow. So yeah. All right. Oops, I did it again where I exited full screen. It happens from time to time. We also talked a bit about some case studies and applications of cryptography. So for password hashing, we want to use salted slow hashes in order to make the adversary's life more difficult. We talked about snake oil crypto. So just in marketing, we have a lot of buzzwords that make people sort of fall over and give you money. If you see something like large keys, new protocols, fancy terminology, stuff along those lines, that's probably indications that maybe the cryptography isn't as new or as fancy as they're trying to make it seem. And finally, we talked about nothing up my sleeve numbers. So constants in algorithms, sometimes you just need to start with some ones and some zeros, and you want to choose numbers with human significance just so that it's clear that no, there's no backdoor here because of these numbers. It's just some numbers that I needed to choose. All right. So today we're going to talk about Bitcoin. I'm sure if you are at all invested in either finance news or technology news, you've heard a lot about Bitcoin. We're going to talk a bit about the construction of Bitcoin, how it all works, some of the cool features of it, and some of the kind of annoying features that maybe make it impractical in reality, depending on your point of view. Sorry, I have some allergies from my pets today, so if I clear my throat or cough a lot, that would probably be why. Just a quick intro. All of this is started by someone called Satoshi. We were talking about how to pronounce it. I don't know, Nakamoto. He wrote a white paper on Bitcoin. So just like basically this is how one would go about constructing Bitcoin. No one actually knows who he is because this is just a pseudonym that he uses, some sort of nickname that we don't know his real identity. And he's very rich because he has a lot of Bitcoin, but he hasn't actually transferred his funds out of Bitcoin into some real currency. So we don't actually know who he is. It's a mystery person behind this really complex protocol. So that's just something that's interesting. Okay, so When we're talking about a way to transfer money, we first need to establish, how do I identify who someone is? If I want to transfer money to Perrin, how do I know who to send money to? How do I even know who Perrin is? So we're going to say our problem statement is that, let's just say there are 4 people, Alice and Bob, they're here from before, as well as Carol and Dave. They each have some amount of currency. Each person can send money to someone else. So for example, maybe Dave and Alice went out for dinner. Alice paid for dinner and Dave is paying Alice back by giving her 10 coins. How does Dave actually give someone 10 coins? In this case, we need to make sure Dave's balance decreases by 10 and Alice's balance increases by 10. That's just kind of how paying people works. And we also want to make sure that no party can spend more currency than they currently have. So if Dave only has 10 coins, Dave can send Alice those 10 coins, but we want to make sure that he can't send 15. So we need to establish some way of making sure anyone can check that Dave has enough money to send some amount of money to someone else. We're going to establish, how do we determine how much money Dave has? And this is sort of the key here. No one trusts any other party and there's no central authority. So it's not like I can just ask the bank, hey, how much money, like, can Dave really give me $15? Because there's no one that I trust. I only trust the fact that everyone's running the same algorithm. And we'll get into how we trust that in a moment. So, if we're dealing with US dollars or euros or your government currency of choice, we have a central authority who is a bank. Maybe it's run by the government, and they keep track of balances and everything, but we don't have that in this case. So we need instead to use cryptography. Okay, so when we're talking about establishing identity, here are 4 characters. 2 of them are based off of real people. You might be able to guess who they are. The first idea is maybe we can use certificates to verify real-world identities. That gives us a really clean way of attaching, hey, this public key belongs to Perrin. Can anyone think of a problem with this? Why we maybe wouldn't want to use certificates? And think back to what we established earlier for what we wanted out of Bitcoin. Yep, certificates use a certificate authority. There's someone out there who we trust. We don't want to trust anyone. So we can't use CAs, so we can't really use certificates. Instead, we're sort of just going to sidestep the problem. We're going to say, like, Perrin and I don't exist. The protocol only sees public keys. So I'm not sending money to Perrin. Instead, it's just my public key that I have control over is sending money to Perrin's public key. So instead of transactions between people, we're just doing transactions between public keys. And we're just going to pretend that real world identities don't exist, and that helps us sidestep the problem. So in this case, you'll see in the rest of these slides, instead of Alice, Bob, Carol, and Dave, we're just going to work with PKA, PKB, PKC, and PKD. And these names are going to sort of step into the background. They don't really exist for this protocol. All right. So each identity is a public key. Next, we need to work out, okay, how do we make one public key send money to another? Just for now, we're going to assume that there's some trusted public ledger out there. So a ledger is accessible to all parties, so anyone can just go and look up, what is currently on this ledger. A ledger is append only, so anyone can add data to the ledger. I can just, write some data on the ledger, but I can't change anything in the ledger. And that gets into the next point. It's immutable. I can't go back and say, like, oh, instead of $10, I'm erasing it to say $1, or maybe adding a 0 to say $100. I can only add data to this ledger. You may notice this is a central authority for now. Just sort of accept this for now. We're going to get into how we deal with this in a moment. But let's just say we need the central authority for now. Okay. How would we record transactions in a way that everyone can see them? Well, we know that everyone has access to this same piece of data, so maybe we can just say, okay, PKD, Dave, paid PKA, Alice, 10 coins on the ledger. So if anyone sees PKD paid PKA 10 coins on the ledger, they'll know that Dave paid Alice 10 coins. Can anyone see any immediate problems with this? If I see that someone put PKD paid PKA 10 coins on the ledger, does that immediately prove that Dave paid Alice 10 coins? No, right. Mallory can just come along and say, oh, hey, you know what? Alice paid Mallory 10,000 coins. So just put that on a ledger and everyone will believe Mallory because there's no way to verify. So what would be the simplest solution to solve this? And just remember that everyone has a public key and a private key that they keep with them. How would you solve this? Yes, exactly, signatures. So what we can do is we'll just sign the statement. So now we have PKD paid PKA 10 coins. And this is signed by Dave's private key. So now anyone can look at the ledger and see, okay, Dave paid Alice 10 coins. And I can, take Dave's public key, verify the signature and see, okay, this checks out. Dave paid Alice 10 coins. So the issue now is, how do we know that Dave has 10 coins to spend? Dave can still come along and say PKD paid PKA 10 coins, or say 10,000 coins, even though Dave is broke, doesn't have any money. And this would still technically be valid. So we need some way of validating how much money does Dave actually have. So we're just going to say this is our ledger version 1, the ledger v1. Let's say the first entry in this ledger is that everyone magically starts with 10 coins. Just pretend that this can happen for the sake of argument. And I'm just going to ask you a simple question. If PKA paid PKC 4 coins, PKB paid PKD 6 coins, and then PKB paid PKA 2 coins, I'm realizing this is getting really hard to say. How many coins does Alice have now? 8. And how did you figure that out? Right, 10 plus minus 4 plus 2. We just went through and did math. So we know that, somehow everyone starts with 10 coins. Then Alice lost 4 coins because of transaction 2. Then Alice gained 2 coins because of transaction 4. So we're going to define that each person's balance is just how much they have ever received minus how much they've ever spent on this ledger. And here's the key. Even though Alice has 8 coins now, the number 8 doesn't actually exist anywhere on this ledger. Instead, we're just saying Alice has 8 coins because if I do math through this entire ledger, I get to the number 8. All right. How much time does this take? If we're talking about efficiency, would you say this is an efficient algorithm? What do you have to do to actually figure out someone's balance using this protocol? All right, we'll just talk about that then. Yeah, linear with regards to all the transactions. This will take far too long. If the ledger is 100 entries long, now I have to go, okay, it's 10 minus 4 plus 2 minus 6. I don't know, some large, I have to scan through all 100 transactions to see, oh, Alice has 5 coins. This is too inefficient for us, considering that we'll never be able to delete entries off of this ledger. We need some more efficient way of tracking this. These animations came out of order, but yes, Alice has 8 coins. So instead of linearly scanning through the entire ledger, we're going to try to build a smarter system. So I guess before we continue, are there any questions on this so far? All right. If you're typing, feel free to finish your question. I'll loop back to it in a moment. So now we're going to say each transaction has inputs, so basically where the money came from or the source of the money, and it's going to have outputs, so who is the money going to? The idea behind this is now that each party only needs to keep track of transactions where they received money. So if there are 100,000 transactions, but I only received money in transaction 943, I don't need to worry about the rest of the transactions. I just need to know, okay, I received money in transaction 943, so I can use this transaction to pay someone else in the future. And a practical example of what this might look like in English is just say, okay, using currency from transaction 2 and 4, where implicitly I received money, I'm going to take the money in there, give 1 coin to PKA, so give 1 coin to Alice, and 2 coins to PKB, 2 coins to Bob. And this statement is all still signed by SKD. So we know that Dave was the one who initiated this transaction. So Dave received money in transactions 2 and 4. Now we're going to consider that transactions 2 and 4 are spent. So we don't need to keep track of this anymore because, these transactions were already used to pay someone else in some future transaction. So we can delete it from our database and never have to worry about it again. We're also now Alice and Bob have an additional unspent transaction. This new transaction here gives coins to Alice and gives coins to Bob. So now Bob can mentally make a note, or I guess on his computer make a note that, I received money in this transaction, and I can use that to pay someone in a future transaction. So in order to validate that a transaction is unspent, this means that we have to make sure that no transaction after A uses that transaction A as an input. So there's a little bit of overhead, but the key is that we never have to scan through the entirety of the ledger. We only ever have to check from that transaction on to the end, which hopefully people are using recent transactions all the time, so we don't have to do really large scanning operations. Finally, if let's say Dave received a lot of money in transactions 2 and 4, we'll just say, pay whatever change you have back to yourself. So you can list yourself as an output and you receive whatever change that you have, so that the input transactions are still totally spent. We don't have to worry about it anymore. For this example, we'll say that Dave received 5 coins. Using transactions 2 and 4, I know that I received 5 coins from those in total. Give 1 coin to Alice, 2 coins to Bob, and we're just going to say give 3 coins to Dave. Now that I think about it, I think this sums to 6 coins, but it's probably okay because the next slide will hopefully make this more clear. So this is a full diagram of what a simplified version of the transaction might look like. In this example, Dave received 5 coins in both of these transactions. They have inputs that we just don't really need to worry about. And they are input into this transaction here, the one that we're focusing on. So we know that we got 5 coins in, so we need to make sure we have, or 10 coins in, because 5 and 5, and we need to make sure we have 10 coins out. So we're going to say, okay, we have Alice as an output, so Alice receives 1 coin in this transaction. Bob receives 2 coins, so Bob is also an output in this transaction. And because we have 7 coins left over, we'll just say Dave, myself, is also a output in this transaction, and Dave will get 7 coins. So now if we look towards the future, we can see that now Alice in the future could use this transaction as an input and pay, I don't know, Carol 1 coin. And Bob can also use this transaction as an input and pay 2 coins using this transaction. So you can see it starts to form a bit of a linked list structure, and it's very interesting. The ledger down here just shows what it will look like, except in text and really long words. So we have the same 2 input transactions here. Transaction 4, which is the one that we're focusing on, says that transactions 2 and 3 are inputs. And it just says give 1 coin to Alice, 2 coins to Bob, and the remaining 7 coins to Dave, myself. And this is the second and I guess final version of the ledger that we're going to look at today. Are there questions on how this works or why we implemented what might look like a more convoluted algorithm? All right. I think we managed to implement a disappear instead of an appear animation today, so it's all right. As before, as I mentioned, each transaction has inputs that we have to verify, and the inputs have to be equal to the output so that we completely spend the inputs, and any leftover money is sent back to the center. All right, so that's great. If we have a public ledger that we somehow trust and everyone somehow has access to, then this is great. This works perfectly for us. We can just implement the scheme and call it a day. But it's not that simple. Remember, we want to not trust anyone. So we can't trust anyone to just maintain this ledger for us because, what if that person is untrusted? What if they're evil and they want to remove my transaction from the ledger, and it will continue on as though I never paid someone else. And then that someone else will be mad at me. So I want to somehow construct a public ledger that doesn't require trust in anyone. And that sounds absolutely crazy, but we're going to see how we do it. Okay, so for a moment, I need us to all go back and think about hash functions. So remember that a hash function can take an arbitrary length of data, so as much data as you want, and squeeze it into a fixed length fingerprint. So maybe my 1 GB file still gets compressed down to 512 bits. It has 3 properties. So pre-image resistance says that it's hard to find the input for a given output. Second pre-image says that given an input and an output, it's difficult to find another input that hashes to that same value. And collision resistance is even more general. It just says it's difficult to find 2 inputs that hash to the same output. In practice, we have this additional sort of property that hash functions look random. That hash functions look random. So what this means technically is that changing the input is going to cause the output to change in an unpredictable way. So if I change the input at all, each bit in the output is going to have a 50% chance of flipping from a 1 to a 0 or from a 0 to a 1. So it's hard for me to produce an input that causes a output to look like a certain way. We'll see why this is important in a moment. So the first construction that we'll look at is called hash chains. What we want here is basically just a data structure that we can compute that has an arbitrary number of nodes, and we can compute a hash over all nodes efficiently. And we only need to be able to append nodes to this. So we don't need to be able to change nodes. We only want to add a node to the very end. Technically, what this says is appending a node of size n. We just want it to take O of n time, linear in the size of the node and nothing else. The idea that we have here is if we want to validate the previous block, we're just going to hash that previous block and include it in our current block. And what this means is that we know that the previous block is going to do that for the block before. The block before is going to include a hash for the block before, and so on and so forth. So I guess by induction, if you're familiar with the principles of induction, this represents a hash over the entire chain. The algorithm for appending is going to be that we take the current block, we hash it, we take that hash and we put it in the new block, and then we're just going to say, okay, now the head of the chain is this new block, and now this new block has a hash for the previous block, and so on and so forth. What this means is that the latest hash is a hash over all the previous nodes. If we were to, for example, change the hash of block 1, or change the data in block 1, that's going to change its hash, which is going to change the data in block 2, which changes the hash of block 2, which changes the data in block 3, and so on and so forth. So the hash depends on all of the data that has come before, and this is a useful property for us. As a data structure, this is really just a linked list with some fancy features. Git uses this in its construction. So if you were in 61B and you had the gitlet project, you probably implemented something along these lines, because each commit is going to contain the hash of the previous commit. And this means that we can't change commits in the past, or else we would end up with new commits in the present. And that's why a git commit can represent the state, both the state of all of the files in the Git repository and all of the history. It has that really useful property to us. Questions on how hash chains work? All right. We're going to take a bit of a detour and talk about Merkle trees for a moment, because it's really just a really cool data structure that we don't talk about much, and this is the only opportunity that we have to talk about it. So we're going to talk about it really quickly. For Merkle trees, we want to be able to modify a node and then compute a hash over all the nodes efficiently. So in hash chains, we only needed to append. In Merkle trees, we want to be able to modify any node that we want. So in technical terms, we're going to say that a node of size n and appending it to a structure with m nodes is going to take O of n plus log m time. So both of these terms are relatively small. We still need to hash the entire node, but if we have m nodes, we want to take it in logarithmic time, which hopefully is fast enough for our needs. So we know that if we were to just hash all of the data at once, we would need to recompute that hash every time we change something. So instead, we're just going to try combining hashes together in a sort of tree format. When we work with computer science, trees always come up. Here's an example of it. What we say is that each node is going to be a hash of the two child nodes' hashes. So this diagram over here just depicts it how it is. So we have all of our data in the nodes down here. These two nodes on top contain just the hashes of the two nodes down below. And then this node at the very top contains a hash of this node. And this hash of the very top ends up representing a hash of the entire data, because say if we changed B2, that changes the hash of B2, which changes B23, the next level, which changes the hash of B23, which changes the root node, and that changes the hash. So changing any of the data changes the hash, which is the property that we want. If we want to modify, the algorithm that we implement is that we modify the block, the data block on the bottom here. We rehash the block, and then we put that hash in the parent node, rehash that parent node, keep going up and up and up and up until we reach the root node. So now we've modified all of the hashes, and we've only needed to take log n time, because we only need to do one hash for each layer of this tree. The result, again, is that the top hash represents a hash over all nodes, and we can modify any node and compute only log number of hashes in order to compute the new top hash. Bitcoin is going to use the linear chain because we want that append only immutable structure, but Merkle trees appear in many other applications. And if you stick around afterwards, I can talk about how Merkle trees are used in Bitcoin, but not for the chain itself. So if you're curious, you can stick around afterwards. Okay, so let's talk about the public ledger. We can just forget about Merkle trees for now. We're going to think about hash chains. We need this public trusted ledger, which has these properties that we talked about, but we can't trust anyone to maintain the ledger for us. What this means is we need some way of coming to something that we call a consensus. So a consensus is really just some way for multiple individuals to reach an agreement on something as a group without any trust in any individual. So I can't just say, oh, Peyrin, could you ask everyone what their favorite color is and let me know what everyone's favorite color is? I don't trust Peyrin in this scenario. And I want us to all come to a consensus in a way that doesn't require trust in anyone, only the group. From now on, we're just going to say that multiple transactions can be put into one block. So we only need to reach consensus for one block at a time, but that block contains several hundred transactions so that we can maintain some sort of efficiency. But we're only going to come to a consensus on blocks every once in a while. Okay, so let's talk about forking attacks. I guess this diagram over here reveals the answer already, but do hash chains allow a group of individuals to reach a consensus? And the diagram's already on the right, so I won't waste time for us to come to an answer, but come to a consensus on an answer, shall we? Yeah. No, Mallory can execute something called a forking attack. Let's say that Mallory paid Alice, or just spent 100,000 coins. If now Mallory can construct an alternate history, let's just say, oh, I'm just gonna pretend that I didn't spend 100,000 coins and then continue with the transactions on from there. So now we have one flow of history where Mallory spent 100,000 coins, as she actually did, and another flow of history where she didn't. And we have no way of determining which one is the correct one. So we need some way of agreeing on which chain is the chain that is the truth. We need to all agree on this without placing trust in any individual. So the scheme that we developed is called proof of work. Before I get into that, are there questions on this or Merkle trees or hash chains? All right. So for proof of work, the construction that we're going to use is that each block, in addition to containing all of our transactions, is also just going to contain some random number. We're calling this number the nonce. I guess it's technically not a number used once, but let's just call it that because that's what they call it in the paper. We're going to say that if a block is valid, the hash needs to start with some number of zeros. So if the hash of a block doesn't start with, say, 4 zeros, this is not a valid block. We should all just ignore it and pretend it doesn't exist. What happens if two non-malicious new blocks are added at the same time making a fork? Is there a way to merge back? That is an excellent question. We'll actually talk about this a couple slides from now. So just hold on to your question, and then if we don't talk about it, or if we don't answer your question by, it'll be pretty obvious where that question is answered. But if it's not answered after that, feel free to ask it again. So we say that a block is only valid if its hash starts with a number of zeros. And if we're talking about the properties of hash functions, if we want it to start with, say, 4 zeros, then each nonce only has a 1 in 16 chance of creating a valid block because each of those bits only has a 50% chance of being 0, and we want all of them to be 0. Because we don't have a centralized public chain, we're going to say that each user is just going to keep track of their own blockchain. We say that users will mine a block, and by mining, we say that they just keep trying random nonce values until a valid block is found. We have to try a lot of different nonces because each nonce is going to have, a 1 in 2 to the, 30 chance of creating a block with the correct hash. So we just have to keep trying nonce values until we find something that causes the block to create the correct hash value. So once you find a valid block, say, in this example over here, we need to use the number 17 in hex to create this entire a block with the hash 0000. We're saying we're looking for 4 zeros here. Once we find it, we broadcast it to everyone else on the network. You basically say, hey, I found the nonce that you need to use. And when someone receives that valid block, say, hey, I see that you found a valid block. I'm going to add that to my own chain. And now I'm going to start working on the next block. Again, remember that the blockchain is a hash chain, so each block is going to contain a previous block's hash. So even though this hash has a special property of having 4 zeros in this case, it still represents all of the data in the blockchain that has ever existed. Okay, so this all sounds like a really confusing construction because it's just like, okay, well, now everyone's just hashing a bunch of things until they find a bunch of zeros. How does this help us reach consensus? Well, we're going to say that as our consensus scheme, the longest blockchain is the true blockchain. All right, how does this help us? Well, we know that everyone is going to mine. We're saying that everyone is going to mine on the longest chain they know of. So if I have, one chain that's 10 blocks, and then maybe there's a fork, but that's only advanced by 3 blocks, I'm going to only work on the 10 block chain. instead of the 3-block chain. If we hear about a longer chain, let's say, oh, someone else found a block for a chain that's actually 15 in length, we're actually just going to work on that one instead. The key is that the more people that agree to some really long chain, the more work is done on that chain. And by work, I mean that that chain has more people working on it, so it has more hashes per second that are working on finding, the next block for that chain. So the more mining is done on a chain, the faster that chain grows. So now this longest chain that we have is the one that's growing the fastest. And this foils the forking attack. If Mallory somehow wants to fork the blockchain, create a separate chain that's also valid, she has to create blocks faster than the current existing truth. But this is difficult. If, say, 10,000 people are working on the longest chain, Mallory has to somehow find blocks that are at a rate faster than those 10,000 people collectively can find blocks for the longest chain. So Mallory has to do more work than all 10,000 other people combined. And that's the entire scheme. We say that as long as everyone is honest and everyone is working on the longest chain that they know of, this scheme gives us a consensus thing. We just say, okay, because this chain is the longest, this chain is being worked on the fastest, so it's probably going to be stable because it's hard for anyone to outcompete everyone else who is working on the true consensus algorithm. Any questions on how this works? And Nicholas, hold your question. It's going to be answered on the next slide. All right. Let's talk about some examples of how this really comes into play. So let's say that two miners are working on two blocks at the same time, and they append it to the blockchain at the same time, causing a fork. So miner A found, oh, this block with this nonce creates a low enough hash, but it has a different history than miner B, who found another block with another nonce that also has a low enough hash. So suddenly we have two blocks at the same time that, they're the same length, and no one knows which one is the truth. So how would this be resolved? And let's say, we don't have to resolve it right now. Maybe we can resolve it a while from now. How do you think this would be resolved, let's say, by the next time the next block is mined? Let me pose a different question. Let's say that chain A, suddenly, next someone finds another block and broadcasts that to everyone. What happens to all the miners on chain B? What do they do once they see this longer chain? Sucks to suck. Maybe, yeah. All the miners working on B, when they see, oh, there's a longer chain that I just heard about because someone just found a block for chain A, they're going to say, okay, abandon chain B, everyone's now hopping onto chain A. So this will resolve not now, but it will resolve the next time a miner appends to one of these chains, and we just say the longest chain wins. So now this other chain of the fork is no longer valid. Okay. If a miner included a transaction in the latest block created, so someone finds a block, puts it on the blockchain with your transaction in it, are you guaranteed that your transaction is forever in the blockchain? Yes or no? No, right. Maybe someone else was working on a different block and they appended it at the same time. So, one half of the miners know block A or chain A with your block in it. One half knows chain B without your block in it. If chain B ends up winning and broadcasts their longer chain before chain A, then your block basically no longer exists because no one is working on it anymore and your transaction doesn't exist anymore. What this means is that to say a transaction is really confirmed, that it really happened, we have to wait for a couple more blocks to be appended to your chain to ensure that hopefully, if my chain is 10 blocks long at this point, someone's not going to come along with an even longer chain. It's going to say it's improbable that my 10 block chain would have lasted for so long. All right. What if a miner who just mined a block says, no, I don't want to include your transaction. I'm going to work on someone else's transactions instead. Are you completely out of luck? Are you never going to be able to confirm your transaction ever? And Nicholas, I'll answer your question in a moment. All right. In this case, we'll say, okay, that miner didn't include my transaction, but it's basically just whoever finds a block first. So hopefully, there's someone out there who is including my transaction, and they will be the ones who win, and they include your transaction in the blockchain, and then your transaction is confirmed after a couple more blocks. Nicholas, yes. So if you are on the shorter chain and like everyone migrates to the longer chain, at that point, yes, that block doesn't exist anymore. So someone else has to put in work to add that transaction to the blockchain again. It's like that block never existed. All right, so, okay, now we have the scheme that helps us, arrive at a consensus. And if a fork happens, at some point, we will reconverge on agreed upon values. So that's really nice. But how do we actually get these miners to want to mine? They're using their graphics cards or their ASICs or other hardware to perform millions and billions and trillions of hashes per second. What's in it for them? The ivy gets added to the previous block to make the hash. Yeah, each block is going to have a nonce, and you have to find the correct nonce value that gives it a certain number of zeros in its hash. So each block has its own nonce. Yeah. All right, so what's in it for the miners? We want to incentivize them. And because we're working in cryptocurrency land, Bitcoin land, we're just going to say, okay, miners will receive Bitcoin. In this case, we say that each transaction is going to have some small fee given to the miner of the block. So for the outputs, we'll also say, okay, Alice gets 3 coins, Bob gets 3 coins, and whoever mines the block with this transaction also gets 0.0001 coins just for their labor, for the effort that they put in. We also say that each block can give some number of free coins to the miner of the block. So the miner, in addition to changing the nonce value, also has their own bonus transaction that says, oh, PK Alice receives 25 free coins out of thin air. That's just to give them an even larger incentive to make sure that they that enough people want to mine blocks for the blockchain. As more miners join the pool, because we're giving these incentives, the algorithm has a baked-in mechanism that adjusts the number of zeros needed to mine a block. So because we want to say, okay, we want each block to take about the same amount of time, if there's more hash power, so more hashes per second happening all over the world, then we increase the number of zeros just to say, okay, we want to stay at, say, 10 minutes per block. Even if the hash power triples, we always want 10 minutes per block. So we add a couple more zeros for the required amount. And this is just baked into the algorithm. And because everyone's using the same algorithm, everyone will just sort of implicitly know at the same time, oh, now we need more hash power, or now we need more zeros. Questions on this? Contents of the block have to be decided before you start mining for a nonce. Yes, exactly. In theory, it's a little finicky. In theory, you could change the contents because you're changing the nonce. You might as well change something else. So you could add an extra transaction if you wanted to, and then you've already failed for the entire past time. So if you're changing the nonce, you might as well change something else before you continue hashing. So you're allowed to change things. It's just at some point, if you find a block with the correct nonce, those transactions are fixed, because if you then change the transactions, then you change the hash and the block's no longer valid. So yeah, yes and no. How do we attack proof of work? The main attack that you might see around on the internet is something called the 51% attack. And this is hopefully fairly straightforward from the proof of work scheme that we talked about. If some attacker somehow manages to control 51% of mining power, so a majority, they can basically rewrite history and perform a forking attack. So we don't want this. This creates some person out there who has control over the network, and we don't want that. The point of Bitcoin is to create a network where no one has power, but other people can still pay people. So because of this, now this entity has the power to refuse transactions or basically not allow people to use their funds. So this is not something that we want. In theory, proof of work makes this difficult because 51% of the world's computing power is, in fact, a lot of computing power. It's hard for Mallory to compete with the 7.8 billion people on Earth and somehow have more power than the rest of them combined. So in theory, this makes it difficult. The security, in fact, relies on the fact that no one controls 51% of computing power. And we'll see in a moment why this might not necessarily be the case. So that is the construction of Bitcoin. That is basically all of the technical detail that you'll learn about it. Are there final questions on how Bitcoin works before we get into some glaring issues with cryptocurrency in general? All right, what time is it? I wonder if we can take a break. 4:27. Maybe a bit later. I'm a little concerned about time, so we'll see what happens. All right, the trouble with Bitcoin. First one, centralization of power. In theory, Bitcoin is decentralized because no one has like control over the network. But in practice, a few small groups have a lot of control over the system. And this is created by something called mining pools. Because Bitcoin is based on a lottery system, it's basically whoever finds the block first gets the reward. This forms systems where instead of, whoever finds it gets it, they just say, okay, let's say if anyone in this class finds the correct block, they'll just split the rewards over everyone. And now all of our power is pooled together and we have a more stable income. So a mining pool gives steady but smaller rewards. And this is generally what you want because in practice, mining a block is like winning the lottery. It's probably not going to happen. And what happens nowadays is that there are only a few large mining pools and they have most of the control over the power of Bitcoin. So in this diagram here, there's btc.com, which is one pool, F2 pool, which is another pool, and a couple others. And we see that, just these 4 pools here, not counting this one, this is just unknown. These 4 pools here actually make up more than 51%. They control 55%. So if somehow just these 4 pools worked together, they have control over the entire network. Because the point of a pool is that now you're not mining blocks for yourself, you're mining blocks for some controlling entity of the pool, and then that entity pays you back in Bitcoin. So they get to decide what transactions go in, and then they, in theory, if they work together, if they have more than 51% or more than 50%, then they have control over the network. So this makes the 51% attack possible, and is not something that we really want. There are other cryptocurrencies that try to get around this, but that's sort of way out of scope. So if you're curious, you can stick around afterwards. Another centralization power has to do with the code base itself. So these are, someone has to write the code for Bitcoin, and these are generally maintained by some group out there. In theory, these groups have control over the code. So while they don't have control over the network itself, they have control over the code that runs the network. So for example, when we're for Ethereum, which is another cryptocurrency with a couple extra features, when they were hacked, the developers kind of just updated their code to get their money back, which seems to go against the entire point of cryptocurrency. The point of cryptocurrency is no one has the control to do this, but if you can update the code that everyone's running, suddenly you do have this control. And there are also some cryptocurrencies that are just not decentralized by design. So we have something called a private blockchain. What this means is that we add this extra requirement. Anyone can verify a block, but only blocks signed by some trusted private keys are valid. So you need the private key to actually be able to generate a block. This means that only central authorities can sign blocks, even though anyone can validate them. And this kind of defeats the point of decentralized consensus. The only thing you really get here at this point is that anyone can see the blockchain, so anyone can see all the transactions, and you can't really reverse them because the transactions still need to be signed by the private keys. But at this point, if you have some controlling entity that can say not allow you to pay someone else, that starts to defeat the point of this consensus. So in general, Bitcoin specifically and a lot of others don't have as much decentralization as we would like. Questions on this? All right. Another issue with Bitcoin is pseudonymity. So Bitcoin is what we call pseudonymous. What this means is that multiple actions can be linked to a single identity. That identity is not your real identity, but it's a pseudonym. So basically, if I'm paying Perrin, I'm not paying Perrin per se, I'm paying some public key out there in the world. And any transaction to that public key is linked to that public key. I can see, oh, it was this public key that was being paid, or this public key that was paying someone else. In Bitcoin, the pseudonym is the public key, and you can link transactions to that public key. This means that Bitcoin's not necessarily anonymous. So I know anonymity is something that's often, a selling point, what people say is a selling point for Bitcoin, but anonymity really means that actions just cannot be linked to your real identity. So with pseudonymity, in theory, if you only ever use Bitcoin in an unpredictable manner, then no one can say, oh, that public key actually belongs to, say, Perrin or Nicholas. But if you don't do that, your public key can be linked to you. So if, say, your shopping habits are predictable, I know that, if, for example, Perrin always goes on Amazon and buys sneakers, I don't know, at 4:15 in the morning, then I can see, oh, if there's a transaction to Amazon's public key at 4:15 in the morning, then it's likely that that public key belongs to Perrin. So now I know Perrin is doing XYZ, and that's not anonymous. Also, if you ever want something that's not Bitcoin, but maybe, say, a real currency like dollars or euros, then, at some point you have to say, okay, pay Nicholas, and this is his bank account info, and here's his social security number, maybe. And at that point, they can identify you because they know, okay, I received money from PKN and gave currency, gave dollars to their bank account. So now I know who this public key is linked to. So in practice, Bitcoin is not really anonymous, and it's pretty easy to de-anonymize people on the blockchain. Bitcoin is also terribly inefficient. Proof of work is really just a bunch of hashing a lot of the time. We just need to hash things until a hash starts with many zeros, so it takes a lot of work just to literally do anything. It's also really inefficient when it comes to storage because we need to store the entire transaction history just to be able to validate transactions in order to be able to do anything. So there is an alternative where you don't store the transaction history, and instead you ask someone else to send you that history, but now you're trusting that someone else to either send you that history correctly or verify it correctly on your behalf, and that creates this centralization issue again. So it's not as decentralized if you really want it to be decentralized. you need to store the entire blockchain, which I think now is like a couple hundred gigabytes. So it's quite large. And the result of this is that Bitcoin has really low processing capacity. The design limits blocks to about 1 megabyte in size just to prevent spam. And this means that Bitcoin can really only process 3 to 7 transactions per second on average, because you can only fit so many transactions in a block, and you can only mine so many blocks per minute or per second. That inefficiency also leads to really like monstrous amounts of electricity consumption, because we're using electricity to compute hashes for nothing. This, in conjunction with the incentives that come with, you get free Bitcoins for mining Bitcoin, creates a huge amount of energy waste. So people want these mining rewards. And the issue is that if mining becomes more efficient, say we come out with more efficient technologies, that just means that we're hashing at a faster rate, and Bitcoin will automatically adjust to become harder. So suddenly we're not efficient anymore. We're just computing even more hashes. So it's sort of, there's no way to escape from the massive amounts of electricity use if you're using proof of work. Bitcoin uses more electricity currently than the country of Sweden and the country of Ukraine and Norway and Argentina, which is a lot of electricity. It's nothing compared to, like, say, the US or the UK, but it's still a lot of energy that goes into hashing that ultimately doesn't actually do anything other than prove work. So it's kind of, not great, especially for the environment. There's also the issue that, Bitcoin is irreversible. We said that this is kind of what we want, but if we think about modern banking transactions, these are designed to be reversible. If we not commit fraud, if fraud is committed against us, and someone stole money from you, you can call Chase or call Wells Fargo or whoever your bank is and say, hey, can you help me get my money back? And they'll say, yeah, we can look into this. Maybe we can reverse the transaction and so on and so forth. With Bitcoin, if you call, I don't know, the inventor of Bitcoin somehow, they'll say, sorry, we can't get your money back. There's no way to do that. Once Bitcoin is sent, the transaction cannot be undone because it will live in the blockchain forever unless they decide to send the money back to you. But if they're stealing money from you, they probably won't do that. And the other issue is that you only need your private key to access your Bitcoin. So if suddenly, one day your computer gets hacked, or even you just leave your computer open, they can steal all of your money. And because you can never reverse a Bitcoin transaction, your money is gone forever. This means that it's dangerous to store Bitcoin on any computer that is connected to the internet, which is kind of annoying because oftentimes you want to spend money and you'll need to, like, I don't know, pull out your offline storage just to be able to spend money. It's just annoying and it's not very practical. So those are sort of the technical issues with Bitcoin. Are there questions on this or the energy consumption or inefficiencies slides before we continue? All right, that concludes the technical portions. We're going to talk a bit more about how Bitcoin in practice tends to be a little bit broken sometimes. For proof of work, if you look at it from an economic perspective, it's really not great. Wouldn't you need to hook up your computer to the internet to spend money? Yes, you would. Yes, that. So if you hook up your computer to the internet, if you want to spend money, you have to expose yourself to potentially losing all of your money irreversibly without any chance of getting it back. So it's kind of annoying. If we say that proof of work wastes, say, X dollars per hour to defend against attacks, then each user is going to contribute just a small amount of that X. And money is always being wasted, even if the service is not under attack. So if the attacker needs to spend more than X dollars per hour to control the system, or the attacker needs to spend more than X dollars per hour to control the system. And we're assuming, they won't do that because it's costly for them. But if they can make more than, say, X dollars per hour, they will spend that money. If it takes $100 per hour to make $150 per hour of ransom money or stolen Bitcoin, they're going to do that because it's economically viable for them. They make money in the long run. And this is kind of what we see for some services. The attacker can basically just buy computational power from maybe Google or Amazon. I think Google and Amazon and all of those cloud providers specifically prevent this, but you can buy hashing power from different providers. And if the money you spend on those hashing services is less than the money you would make from whatever attack you're trying to conduct, that's going to happen anyway. So we don't have legislation or laws preventing crime from happening. We just have the hope that the attacker isn't going to make more money. But if you have a lot of money, they're probably going to execute that attack anyway. So it's not great when it comes to deterring attacks sometimes. There are a couple other alternatives to proof of work. Proof of work is inefficient and it wastes electricity. But there's this other idea that's sort of the other one you mainly hear of called proof of stake. The idea is basically just that users who have more, not Bitcoin doesn't use proof of stake, but users with more currency have more mining power. The idea is that if you have a lot of stake in the system, if they're at risk of losing money, they're probably more honest. So the benefit is instead of hashing a bunch of things, you're really just staking Bitcoins in exchange for the chance of being able to mine blocks, or validate blocks is the technical term for proof of stake. But this kind of means that if you have more money, you have more control over the system. And that's not great from social reasons. For social reasons, there are often cases where we don't want all the power to be just in the hands of the rich. I'll leave it at that. There's also another idea called articulated trust. This just says, I trust someone else, and that someone is authorized to vote on given transactions on my behalf. So it's almost like federation, federal governments, republics. I'm not great at government things, but you basically designate other people to vote on transactions. And as long as half of the trusted parties are trustworthy, then the protocol is secure. This means that you have to trust someone else. But if you do trust that someone else, then we have that efficiency and energy. We don't run into these efficiency and energy problems anymore. But if you're willing to trust someone, you might as well trust a bank. So none of these are great, but yeah. Blockchain. Almost everyone has heard of this word blockchain at some point, especially if you're a CS major. Blockchain is often marketed as this like really new technology, but it sort of has existed for a really long time. Hash chains were invented over 20 years ago. There were timestamping services that were really just sort of linked lists / hash chains, and those were proposed in the 1990s, 1990. Merkle trees were likewise patented a bit later, or no, a bit earlier in 1979. So none of these are new technologies. With something like private blockchains, these are things that already see use. If you wanted a append-only data structure, then you would use a private blockchain. Like I mentioned, Git is pretty much a private blockchain. You don't actually sign things, but you can sign commits if you want in Git. And this means that no one can change the history unless they have your private key. And everyone knows that your commits will only be signed by the private key. So this technology has existed forever, but it's only just now becoming like a marketing thing. It's a buzzword that's applied to really unrelated problems. And I know I was talking to some people who are, I think, in the blockchain area. There's like a blockchain club at Berkeley. I forget what it's called off the top of my head, but it was a weird conversation. I won't get into it too much, but there's this idea that maybe we should use blockchain for electronic voting, or maybe we should use it to store medical records, or maybe we should use it to deliver vaccines. And this last one is really crazy because the original versions of these slides were like, we should use blockchain to solve the problem of vaccines expiring if they become too warm. And the solution there is probably not blockchain. The solution there is probably to get temperature sensitive labels. So it's a, whenever you hear use blockchain to solve X, you should probably take that with extreme caution. There are definitely really cool and really useful applications of blockchain. I just don't think that vaccines is one of them, but I'm open to being convinced otherwise. Um, there's an idea called smart contracts. This is something that's used in Ethereum. For something like legal contracts, we're following the rules of English and we're writing basically contracts in the fancy speak that lawyers use that us lay people can't understand anymore. For smart contracts, we say instead of using English, we write it in code and we execute that code to follow the procedure. And this code is stored in the blockchain, so we can't actually modify it. It's set in stone, basically. If you've ever written code that was buggy, this code, if you put it in the blockchain, will exist forever. It doesn't really solve that much. Most smart contracts are actually just finance bots. So these are just bots that perform small actions in real money-related actions in real time. So maybe trading bots or something along those lines. And if this code is vulnerable, you can violate the contract. And Ethereum in particular uses a language that's really gross. So buggy code abounds. And we mentioned all the way in lecture 1 that there was a smart contract. You could write a smart contract that would steal money from people because of a time of check to time of use vulnerability. So if you want to go all the way back, you can find that. But yeah, writing contracts in code is probably not a great idea because we have the legal structures to establish binding contracts in English, which we all intuitively understand, and you don't need to understand a code to be able to read contracts. NFTs. This has been a thing in the last, I think it was year. I can't keep track of time anymore, but an NFT is really just a piece of data that say XYZ work of art or file belongs to someone. So you would just sign, oh, this work of art now belongs to some individual signed by the public key of the previous owner, and you store it on the blockchain, and now this asserts that this belongs to the owner, the new owner, forever until they decided to sell it on to someone else. So it's kind of an interesting idea. It doesn't have anything to do with copyrights or sharing of the file, so there's no actual value in NFTs, but this kind of really exploded last year and this year. They've been selling for millions of dollars, which I find kind of crazy because, again, you don't get any value other than the statement exists somewhere in the blockchain that you own this file. But this is an example of how adding the word blockchain to something convinced buyers to invest in it. So yeah. We'll talk about speculative bubbles really quickly. NFTs and also Bitcoin aren't worth anything on their own, but because people think, okay, this will be worth something in the future, they buy it now and the price keeps going up and up and up. And at some point the bubble bursts and everyone realizes, actually, maybe we should just sell these because maybe it's not worth it. And then it crashes, the price of say Bitcoin or NFTs crash, and then it either goes into obscurity or forms another bubble. It's kind of, if you check the graph of the price of Bitcoin recently, you can see, I think it had a bit of a crash a month or two ago. I don't remember off the top of my head. There's also censorship resistance. This is more of a Nick slide, the normal instructor for this course, other than me, because I kind of like censorship resistance. There's a time and a place for it, but the key point of it is that Bitcoin doesn't have a central authority to block transactions. So anyone can pay anyone through this electronic payment, even though like PayPal or Zelle or Venmo would block it because it's for some illegal thing like drug dealing or whatever. WikiLeaks, which is an organization that publishes classified information, they're used by whistleblowers to expose governments and corporations and whatnot. They tend to be censored by governments because, governments don't want their secrets being released. Um, and you can only use, I think you can only, I'm not sure, but you can use Bitcoin to support WikiLeaks because most payment companies won't pay WikiLeaks because they're kind of, the government is opposed to them, and the financial institutions don't want to support institutions that the government opposes. So Bitcoin is the only platform that you can use to pay WikiLeaks because it has no central authority. There's also the idea of crime because you can use it for very, very illegal transactions. And I'll sort of let you think about what all these examples would be on your own. But again, because there's no central authority, there's no rule, there's no one that can impose a rule that you can't pay someone for something. So it kind of ends up being the way that people ask for illegal transactions because anything that is, uses dollars or euros or whatever, those would just get immediately reversed by the financial institutions, and then they would be immediately arrested for this transaction happening in the first place. There are a couple other alternatives. I don't really feel like talking about these because again, censorship resistance and sort of the crime it enables, I have a slightly different opinion than these slides expose. So, and it's blue, so I don't really care about it. What I do care about is volatility. This sort of has to do with the marketing thing I mentioned earlier, but the value of Bitcoin tends to change really quickly because it's not actually tied to anything that's valuable in the real world. So you can get these price shocks where the value changes all of a sudden. If there are more transactions than than you can fit in one block per unit time, the price of transactions goes up. So these users are just saying, okay, I'll pay you half a Bitcoin to include my transaction. Okay, I'll pay you 75 or 1 Bitcoin to include my transaction, and so on and so forth. So you're competing for a limited number of transactions that can never change because this algorithm is sort of fixed. There are also attacks that we've seen that where people deliberately cause high demand for transactions, and this causes the price of transactions to go up, and maybe that causes Bitcoin to no longer be accessible to those who can't pay high prices to have their transactions count. So again, we're running into the problem of those who have money can use that money to block others from spending their money, especially the poorer. So again, we have social issues baked into this as well. The result is that Bitcoin is seen more of a stock than a currency. Users will hold on to Bitcoin just to grow their investment, but we don't see that much use for it as a payment method. Although we have seen a couple of developments for that. So again, you can also ask me about those afterwards if you're curious. Speculation. Are there any? I think it's 4:54. I think we've got time. Because of volatility, like I mentioned, you can get speculation where they're thinking, okay, it will be worth more later, so I'll just buy some now. You don't buy Bitcoin because somehow owning Bitcoin helps you make more money. You just buy it so you can sell it later for more money. This sort of relies on price changes instead of this long-term value for something like gold or even the US dollar, because that's guaranteed to probably be worth something in 100 years. This results in, as I mentioned, the bubble where something keeps selling for more and more of it, more and more. And at some point it goes above its true value, which for Bitcoin is 0. And at some point it bursts and people say, okay, this is not actually worth anything. I'm just going to sell it off now. And then everyone's like, oh, everyone's selling it. I should sell it now before the price drops too much. And then oftentimes these bubbles have caused huge economic losses. Not just Bitcoin, there are other bubbles that have happened in the past. I'm sure you can look it up. But yeah, the economics of Bitcoin are also not great sometimes. When we're trying to exchange Bitcoin for something that is officially worth something, we'll use exchanges. So if we want to buy a product in Bitcoin, what's going to happen is that the buyer just takes their $5 turn it into Bitcoin and send that Bitcoin on. No one's actually holding onto Bitcoin for the purposes of buying things. The seller receives this Bitcoin and just turns it back into the standard currency. So users need ways to be able to exchange these Bitcoins for other currency, but that's difficult, again, because Bitcoin transactions are irreversible. So we run into fraud problems and whatnot. So if the buyer wants to buy Bitcoin from someone, if the buyer sends money and then the seller never sends Bitcoin, the buyer is sort of out of luck. The seller must trust that the buyer will pay them. So if the seller transfers Bitcoin first, if the buyer never pays them, then you're also out of luck again. So there are ways to get around this. If you use something like cash, then both parties are sending something that they can never get back. So it's sort of okay then. If you trust the seller, so let's say now I trust Perrin, and Perrin has some Bitcoins. I know he probably won't scam me. So I can buy Bitcoin from him, and hopefully when I send him my cash, he'll actually send me Bitcoin. Or you can do a deposit. So basically you just send a bit of money and then they send you the Bitcoin and then you send them the rest of the money. Okay, that brings us to the end of problems and whatnot. I think, maybe not. There are some other cryptocurrencies. So you may have heard of some of these. Most of them are basically the same thing with some different algorithms or maybe a couple of different principles. Some of them are radically different, but we won't get too much into those. They use the same ledger, which has a decentralization focus. And some are literally just forks of the original blockchain. So they have the same history up to a point, and then at some point someone modified the software to say the fork ignores Bitcoin and the Bitcoin ignores the fork. So now they have two different histories, but they have, the same root. All cryptocurrencies, or most cryptocurrencies, sort of are just Bitcoin with a different thing attached to it. So Litecoin is just Bitcoin with a catchy slogan. Dogecoin is Bitcoin with a joke. Ripple is a centralized cryptocurrency that has some additional settlement structure. IOTA is kind of I don't even understand it. They say they designed their brand new cryptography using trinary math instead of binary math with like bits and whatnot. So who knows? Monero improves the pseudonymity. I'm not sure about this one. It might also be anonymous. There's Zcash, which is built on top of Bitcoin and adds real anonymity using really complicated cryptography that I won't even begin to try to understand. And Ethereum adds rewards for catching bugs because it has so many bugs in its smart contracts and other aspects. Yeah. For cryptocurrency, because there's so much hype around it, it's often seen as like a get-rich-quick scheme, and this leads to frauds, which will sort of happen with any get-rich-quick or any get-rich-quick perceived schemes. So a lot of the frauds that happen in cryptocurrency are just frauds that have happened way back in the day, but now because there's no more regulation, they can happen again. So Ponzi schemes, these were a thing a while ago. But you just trick uninformed consumers to invest in a non-existent product. And because if you invest with Bitcoin, you can never reverse that transaction. There's no way to get your money back. There's wildcat banks. So banks that sort of don't use the federal government and they just sort of use their own money. If your bank shuts down, your money is gone forever. And in the cryptocurrency exchange, in the cryptocurrency scene, if your cryptocurrency bank decides to just shut down and take all of your money, there's no way that you can do to avoid that. Physical banks, wildcat banks used to exist in the 1800s, but they were legislated out of existence. And now that cryptocurrencies are a thing, this exists again. For unregulated securities, sometimes these are just stocks that the government has no control over. The unregulated stock might be completely worthless, so it might also be a Ponzi scheme. Or you might say, okay, I'll pay money now in exchange for some coins when the cryptocurrency launches later. So let's say, oh, I'm designing a coin, let's call it Evan coin. and I will give you 100 coins from now if you invest, say, $1 million in me. And then I take your money and never get it back. So yeah, all of these scams have sort of existed for forever, and then they stop existing because they were made illegal. And now cryptocurrency makes them possible again. So the point of this is just that there are a lot of drawbacks when it comes to using cryptocurrency and using something that no one has control over. Because if you think about it, the harder you think about it, the more you realize that maybe you do need trust in some entity. So, sorry, we've gone completely over time. Well, not completely, it's 5:01. Just to summarize, we want a currency system that doesn't rely on any central authority. We have transactions, or we have identity that each user has a public key. Transactions, so you can send money between public keys. A public ledger that where we put all of the transactions. So we say someone paid someone else using Bitcoins from some previous transaction. And this is constructed using proof of work. So instead of someone maintaining a ledger somewhere on a server, we say that everyone agrees on the same ledger because whoever is working on the chain, or whichever chain is longest, has the most people working on it. And whichever chain has the most people working on it grows the fastest, so it will maintain steady. So this is how we reach our consensus. There are a lot of issues with Bitcoin. It's more centralized than we would like it to be because we have mining pools that have a lot of power over the cryptocurrency. For pseudonymity, you can link your transactions to who you are if you're at all predictable. So it's not great for anonymity. It's really inefficient. It spends a ton of money just hashing things in order to maintain the consensus. And you need to store the entire blockchain, which at this point is hundreds of gigabytes. And it's irreversible. So if you lose your Bitcoin, you will never get your Bitcoin back. Whew. Okay, that was a lot. I thought we would end earlier than this, but I guess not. That is all that we have for our lecture today. Good luck with the midterm tomorrow. And yeah, feel free to stick around for questions, and otherwise I will end the recording.